Hello everyone, we are very grateful to share our paper named High-Dimensional Dataset Simplification by Laplace-Beltrami Operator on CGI 2021 conference. The speaker is Chen Kaish, and the corresponding author is Hongwei Lin. We are both from Zhejiang University. The presentation includes 4 parts. At first, I will briefly introduce the background of our research. It is well known that big data concerns large volume, complex, and multiple sources. Nowadays, with the development of the internet and other digital technologies, larger amounts of data are generated at a speed greater than the data processing of human beings. The purpose of dataset simplification is to maintain the maximum amount of information a dataset contains, and at the same time deleting the maximum amount of the redundant information. Therefore, dataset simplification is a feasible method to process a big dataset while using a limited data processing capability.
However, high-dimensional dataset simplification is still a difficult problem, considering dataset simplification method that does not change the form of data sampling and topological data simplification are the two most common methods, but these statistical and topological methods also have limitations. For example, stratified sampling, atomic link, and SMOT are usually designed to solve the imbalanced data problem in classification. In these methods, the label information of data is needed before the sampling, but this condition is not satisfied by all datasets. For another example, the topological methods, such as RibbSpace, ContourNet, and Mapper, are more suitable for low-dimensional data. When the dimensionality of the data is too high, the computation cost will become unacceptable. The more serious problem is topological methods extract the topological structure from a given dataset, and these structures require new representations, which is different from the original data. Then, the legality of the new topological structure is generally not guaranteed, especially for image and text datasets. The extracted topological structures are often not images and text. In this paper, we develop a high-dimensional dataset simplification method based on future point detection using the eigenvectors of Laplace-Beltrami operators. Moreover, we devised 3 metrics for measuring the fidelity of the simplified dataset to the original dataset. Finally, we discuss the capability of the proposed method using several examples and applications. Now, we start to introduce our method. Let M be a manifold with a Riemannian metric, and F is a real-valued function defined on the manifold. The Laplace-Beltrami operator on manifold is defined as the divergence of the gradient of F. That is equation 1. Further, Laplace-Beltrami engine problem is defined as a second-order PDE on the manifold, which finds real-valued functions and real numbers satisfying equation 2. The family of eigenvalues is an increasing sequence, which is also called spectrum. Their corresponding eigenfunctions are defined on manifold. The important thing is the eigenvalues specify the discrete frequency domain of a Laplace operator, and the eigenfunctions are the extensions of the basis function in Fourier analysis to a manifold. Eigenfunctions of larger eigenvalues contain higher frequency information. The solutions of eigen problem are widely used in many applications, such as geometric processing and high-dimensional data processing. In this paper, we use the local extrema of the eigenfunctions as the future points of the dataset, which constitute the simplified dataset. In this paper, the given dataset is represented by a high-dimensional organized point cloud. To calculate the eigenvalues and the eigenfunctions of the eigen problem, the equation must be discretized into a linear system. We use the discretization method developed in Laplacian eigenmappers to construct the discrete operator, which is a common method in manifold learning. The operator discretization method includes two steps. The first step is constructing an adjacency graph. In our method, we use KNN for an point. Its k-nearest neighbors is determined using KD tree. Then, the connections between the point and its neighbors are established. Thus, the adjacency graph is constructed. The second step is computing the weight matrix. Using the adjacency graph for all points in the given dataset, the connections between points and points are established. Then, the weights between points Vi and Vj can be calculated as follows. Now, the Laplace-Beltrami operator can be discretized into the matrix as the inverse of A multiplied W. Here, A is a diagonal matrix. Meanwhile, the engine problem is discretized as the second line formula, which is a matrix engine problem. Because the matrix W is symmetric and the matrix A is diagonal, the eigenvalues are all non-negative real numbers, and satisfying that lambda 1 equals to 0, and the corresponding eigenvectors are all orthogonal. Finally, we detect future points on these eigenvectors to form a simplified dataset. In our method, the local maximum, minimum, and saddle points of the eigenvectors are used as the future points. Since the eigenvectors are defined on an unorganized high-dimensional point set, the detection of these points on the eigenvectors is not straightforward. To detect the maximum and minimum points, we use the KN of every point. If the value of a point is larger than its all neighbors, this point is defined as the local maximum point. The definition of the local minimum is the same. The detecting of the saddle point is more complicated. We first project the detected point and its neighbors to a 2D plane. Then, for a neighbor whose value is larger than this point, we give it a plus symbol. Similarly, for a neighbor whose value is less than this point, we give it a minus symbol. Then, we count the number of symbols that change follow one direction. If the counter is larger than a preset value, such as 4, this point is a saddle point. The detection starts from the first eigenvector and adds future points into the simplified dataset. Then it detects and adds the future points on the second vector. This procedure is performed iteratively until the size of simplified dataset reaches the preset value, or the fidelity to the original dataset reaches the preset threshold. So, how to measure the fidelity of simplified dataset to the original dataset? In this paper, we devise three metrics. They are KL divergence, Hausdorff distance, and convex Hall volume. They measure the fidelity from three aspects, which are the entropy of information, the distance between two sets, and the volume of a dataset. The calculation method is introduced in our paper. We won't detailedly introduce them here. Next, we will show some experimental results of our method. At the beginning, we select some dataset for visualization. In the experiment, our method is employed to simplify the four well-known high-dimensional datasets, including the Swiss roll dataset with 2,000 points in a 3D space. The Minist handwritten digital dataset includes 60,000 images. The human face dataset includes about 700 images, and the Siva-10 classification dataset with 50,000 images. For example, in Minist, each image is 28 times 28, which can be seen as a 784-dimensional point. So, the dataset is a 784-dimensional point cloud with 60,000 points. Firstly, we intuitively show the data simplification results. In the first row, the figure A is the original dataset of series row with 2000 points. In Figure B, we detect the future points of the first 5 vectors, which captures the critical points at the head and tail positions of the Swiss row. Figure B2F shows the simplified sets by detecting higher frequency vectors. More future points are added into the simplified dataset, and the set is closer to the original dataset. Similar results also appear in the second row on the MNIST dataset. In order to show the ability of our method, we display the detection results of the first 5 vectors of the human face dataset. The images of the human face dataset were captured by adjusting 3 parameters. They are up to down pose, left to right pose, and lighting intensity. Therefore, the images can be regarded as distributing on a 3D manifold. Specifically, in the first vector, the 2 future points are 2 images with leftmost pose at the most lighting and the rightmost pose at the most lighting. In the second vector, an image with rightmost pose at the fewest lighting is added. Similarly, in the future point set of other vectors, there are more extreme images of the pose and lighting. Next, we show the fidelity curves during the simplification process. For KL divergence and the convex Hall volume, as can be observed that the matrix of 4 datasets rapidly reduced to a small value. One interesting result is that the convergence speed of Hausdorff is related to the intrinsic dimension of the dataset. The lower the intrinsic dimension of a dataset, the faster the convergence speed. For example, the intrinsic dimension of the dataset Swiss row is 2, which is the smallest of the 4 datasets, and the convergence speed of Swiss row is the fastest. The intrinsic dimension of the dataset human face is 3, greater than that of Swiss row, and the convergence speed is slower than that of Swiss row. The intrinsic dimensions of the dataset MNIST and simplification are greater than those of Swiss row and human face, and then their convergence speeds are the slowest. Next, we compared our method with the simple random sampling method. The result shows that under the same simplification rate, the simplified datasets by our method are more fidelity to the original dataset than the simple random sampling method. Finally, we demonstrated 2 applications of the simplified dataset. They are the speed up of dimensionality reduction and the training dataset simplification. The first application used the simplified dataset and out-of-sample method to speed up the linear dimensionality reduction. The results show that using simplified dataset can speed up at least an order of magnitude and maintain similar dimensionality reduction results. The second application can reduce the cost of manual annotation in supervised and active learning. Although training with a simplified dataset cannot achieve the same accuracy as the original dataset, our method still has potential applications in supervised and active learning, such as early stopping. In summary, we proposed a high-dimensional dataset simplification method by detecting the future points of the vectors. The time complexity is independent of dimensions. The simplification rate is easy to control, and the dataset representation is not changed. Moreover, we devised 3 metrics to measure the fidelity of the simplified dataset to the original dataset from three perspectives, and 2 applications of the simplified dataset were demonstrated. That's all for our report. Thank you very much.